All right, in this video, I want to revisit the bathtub filling problem, but for a case where now R, the inflow rate, is a function of time. And to make things simple, we're just going to assume that the flow rate is increasing linearly with time. So the new problem we'll have is the following. The rate of change of the volume in the tank is equal to R of t, and V of 0 is equal to 0, like before. But R of t, where R of t is equal to some constant A times t. So at time t0, the flow rate is B, and then from there it increases. So if I make the graph here, this is time, and here is R of t. So it's going to start at B and then increase such that the slope here is A. So delta R over delta T is equal to A. We can check what the dimensions of A and B are. So remember that R is a flow rate, has dimensions of length cubed per time. So that means that A times T is length cubed per time. And so A times time is length cubed per time, or A has dimensions of length cubed per time squared. Whereas B, the dimensions of B has to be an L cubed per time. And now we're going to do the integration, and we're going to use the method that I called Euler Forward before. And now it'll be a little bit more clear what I mean by Euler Forward, as opposed to what I might call Euler backwards. So let me do two examples. Euler forward and on this side, Euler backwards. And remember, when we discretized this equation, we ended up having V at time step n plus 1 minus V at time step n divided by delta t is equal to R. And now, since R is a function of t, it will matter whether we pick R to be defined at time step n, which would be a valid approximation, or at time step n plus 1. And that choice is what's going to decide whether we have Euler forward or Euler backwards. So for the Euler forward, we will do the volume at time step n plus 1 is equal to the volume at time step n plus delta t times R at time step n. This is Euler forward, so we use type step n. So on this side, everything that goes into computing the volume at time step n plus 1 depends only on type step n. Whereas in Euler backwards, we will have V at time step n plus 1 is equal to V at time step n plus delta t times R at time step n plus 1. So if I was to discretize, so what I'll do is I pick discrete values of R. It's going to be defined here. And then if this is at delta t over here, so this is delta t is this time interval. And then at the next time interval is defined here. And then the next one over here. So we'll do both these methods, and as you will see, we'll get a slightly different answer depending on which one we pick. Before we go to the computer and implement these two different schemes, I want to show you what the analytical solution is. So remember, dv dt is equal to R, which is A times t plus b, v of 0 equals 0. So to get the solution, we integrate both sides. So we have the integral from 0 to tau dv dt is equal to the integral from 0 to tau a t plus b dt. On the left-hand side, I have the integral of a derivative, so that just becomes the antiderivative. So I have v times the tau in 0 is equal to, same thing over here, I integrate the integrand over 2 t squared plus b times t from 0 to tau. We can check that this is the correct antiderivative. If we take the derivative of t squared, I'll get 2t, which will cancel the t on the bottom, so I'll end up with at, and the derivative of this term is just b, so I get back what's in the integrand. And that means that v at times tau minus v at 0 is equal to a tau squared over 2 plus b tau. And the initial condition is that v of 0 equals 0, and so the solution is v of tau is equal to a tau squared over 2 plus b tau. So if we plot it, it'll look something like this. So at tau 0, it's 0, and then it increases quadratically. Something like that. All right, now let's go to the computer and compare the Euler forward, the Euler backward, and the exact solution. So now I'm going to get rid of this constant flow rate and just comment it out, and I will define the new flow rate, which is a function of time. So R is a function of time and is equal to a times t plus b. And so now I've introduced two new constants, a and b, which I have to define. So let's define them right here. Let's pick a to be 0.1, and this will be meters cubed per second squared. And then b, it's 0.0001. Let's make it very small. Meters cubed per second. All right, so then we come down here, dt, all these things don't change. And one thing I will change is we're gonna, just for illustration purposes, we're first gonna run it for a very short period of time. So let's just run it for 6 seconds. Only 6 seconds. With the time step of 1 second, that'll be 6 time steps. And then here, what used to be r of t will now be r of tau at time step n. And this is the method called Euler Forward. Euler Forward. And for comparison, I will define another volume, V. This will be volume 1 using the Euler Forward approximation. I'll put an F, and one for Euler backwards with a B. And so here I initialize the Euler Forward approximation and then the Euler backwards approximation. So at time t0, they're both the same. And then here I will define both. So this is the Euler Forward approximation and then the Euler backward approximation. If I want Euler Forward, everything should be defined at the same time, which is 1 less than tau Vn plus 1. So here I have an n, so this should be n minus 1, and this, both of these have the same timestamp. So this one should be minus 1, and this one should be n. So this is Euler backwards. Tau at n is equal to tau at n minus 1 plus dt. So I don't need this extra. All right, so for the Euler backwards, the rate is evaluated at the same time as the function, so at time step n. For the Euler forward, the rate is evaluated at a time step, one time step before v on the left-hand side. Okay, and from there, I can now make my plot. V forward, and then V backwards. So the forward, I will do it in blue, the backwards in red, and then I also need to plot, I would like to plot the analytical solution. So plot tau V analytical, which is, I have it somewhere, is A. Let me just define it here, VA is equal to the function of tau A times tau squared plus B times tau. And this one I'll plot it in black. And hold on. I guess for the analytical one, instead of just plotting at the discrete points, I'm going to plot it at a higher time density to emphasize the fact that it is a continuous solution. So the time, I'll define a time variable that goes from 0 to 6 seconds, but I'll put a very high frequency of sampling, 0.001, so that this one will be a smooth curve. So T and T. All right. So let's try it. Hopefully I coded everything correctly. There we go. Let's make it bigger so we can see. So remember, the black curve, the one that's kind of smooth, let me add some circles. One more things here. For these that are discrete, I'll put circles and line segments. So this is the exact analytical solution, which is kind of smooth, and you can see the other one is kind of piecewise linear segments. And the one that used the Euler Forward was in blue. It's a little bit lower, and the one that is in red, using the Euler Backward, is a little bit higher. And you can see why that is from the form of the solution, right? Over here, you notice that since the rate R is always increasing, then I'm using a slightly faster rate for the Euler backwards than the Euler forward. And so that's why the red one, which is the Euler backwards, is always a little bit higher, because R keeps increasing and I'm using a different time interval to evaluate it. Whereas this one, it's using the beginning of the time interval to approximate the rate, and so it's always slightly underestimating the analytic function. So maybe a picture would be useful. So the integral ends up being the area under the R curve, and so R starts at B and increases like a quadratic. And so when we want to approximate the Euler Forward, we have the function v at this time, and we approximate the rate of inflow using the beginning of the time interval. And so we multiply this by delta t, so we end up finding this area. If this is 1 delta t, this would be what we would do for the Euler backwards. And then we have a new solution, and now we evaluate, so we have a new time step, and we take the rate of flow in at this point, and we advance it for another time step. So 1, 2, and this is now the area for the second one. So this is 2 delta t. And then we take the rate again, and so this area is proportional to the volume at times v forward at times 3 delta t is equal to this area. But if we did the Euler backwards, what we do is we evaluate the rate at time step n plus 1. So we use the end of the interval to calculate the rate. So that means that for the Euler backwards, we're using this volume for the first time step. And then for the next time step, we're using this volume. And for the third time step, well, I'm running out of space on the page, but this would keep going. And we would end up using the rate computed again at the end of the interval, out here somewhere. And so the volume using the Euler backwards approximation until delta 3t will be equal to the red area. Whereas this one is the black area. And of course the analytic solution, well, it uses the exact area. So the analytic one will compute the area exactly under this curve. So the red one, in this case, always overestimates the area under the curve, and the black one always underestimates. And you can see why you have these two different curves for what the volume is as a function of time. Now, of course, if you make delta t smaller, the difference between the red and the blue curve is going to be smaller and smaller. And in the limit, where delta t goes to 0, well, you will recover back the solution you get on the black curve. That's the limit as delta t goes to 0. But you can see now that depending how you approximate things, you get a different answer. An even better approximation would be to use what's called the trapezoid rule. Right? So instead of taking the rate either evaluate at the beginning of the time interval or at the end of the time interval, we can take the average. And then we use what's called the trapezoid. We use this area. And then at the next time step, we use this area. Right, you can see that this will be a much better approximation than either the Euler forward and Euler backwards. So the trapezoid rule integration will be the following. V at times t plus delta t is equal to v at times t plus delta t times, and here I'll use the rate at times t plus delta t plus the rate at times t, and I divide by 2, I just average. So I take the average of the rate here, divide by 2, and I get the average rate. And that's the one, this one is called the trapezoid rule. Trapezoid rule. And let's code that one up and test it, see if it does better. So if I come back here, I'll define yet another V. I have V forward, V backwards, and then V trapezoid, Vt. And so this one is the trapezoid rule. And let's plot that one also over here. So I must give it an initial value. E for the trapezoid rule at time 1 is 0. So they all start at the same place. All right, so there we see our Euler backwards in red, Euler forward in blue, and then the trapezoid in green.